Yeah, so it's a pleasure to have Cheng Chin give the. Am I pronouncing your name correctly?
Yeah.
Yeah.
Perfect.
To give our seminar today. So, you know, Cheng is multiple honors and awards, including both Einstein Condensation Award, American Physical Society Fellow, and others. And is doing many interesting things. And today, he's going to tell us about Bose fireworks. Good to know what it is. Thank you. So,
Great. Okay, thank you for the introduction. It's my great pleasure to be here and tell you about this our recent research. I know most of you are home, just like myself, so you can feel more relaxing at home. I think people even outside enjoy the sunshine and so on. It's great. So I'm going to be also give you not going too much into a technical detail, but just say a story about kind of this our recent research into this new observation, what we call Bose fireworks. So why it is and how it was discovered, and what are the sciences, what are the kind of science project that we came up from this Bose firework experiment. So in the first slide, what you see, this is a Chicago downtown, and we're next to Michigan Lake, and our university on the south side, about this 15-minute driving distance. For those of you not familiar with where Chicago is, you can see here. Now this right here next to the Michigan Lake, and we are essentially just like 5 minutes away from the lakefront. So here's another view of our university right here, and also you can see downtown in the background, the Michigan Lake on the right side. This is maybe here. A few locations I'm going to just emphasize. This is where kind of Enrico Fermi developed, but this is kind of a reaction pile in the 40s. Okay, related to the Manhattan Project. More recently, this the previous president, this Barack Obama's home is still is only like about 10 streets from us, right here. Okay. And our lab is not far away, so we actually moved into our lab about this. Maybe about 13 years ago. It's a new lab space, and I was hired around that time to do this experiment into this coatoms. This is a main quadrangle, you can see, and it's a nice place to live. All right, so this is our website. You can see this are our group members, and you can find our webpage more information right there. I'm just going to give you a brief introduction. So these are group members, the students from the US and from China, Japan, this also India and so on. Okay, and we're postdoc, graduate student. I told you.
We don't always hear you clearly. At least I sometimes.
Can you hear me?
Sometimes the voice is fading. I don't know if it is my problem, but.
All right. I can try to speak a little bit slower and louder and see whether that helps. All right. So, and I will mention briefly what are the kind of main direction of our research in the past couple of years.
Cheng, we also see both of your current slide and your next slide as well. I don't know if that's the way you intended.
Oh, really?
Yeah.
Let me see. How do I change?
I think maybe in the display setting. Or
I see. So yeah, see both.
I see. Yeah, for some reason I see both of your.
I see.
And it's not that such a disaster, but.
It's not a problem, but is the sound you hear the sound fine?
Duplicate slideshow so present here. It is better?
No, it's yeah.
Now it's better.
Yeah.
Now it's better. Yeah. All right. Very good. Okay. So now, so I briefly mentioned our general direction about research in the past about 10 years. Okay. What do we do with by looking at the atoms that we laser cooled and trapped, and study their kind of equilibrium as well as dynamical properties. In particular, we're interested in the direction to do quantum simulation. This is based on the idea that if you have good control over the quantum system 1, okay, you can in principle control the Hamiltonian or the Lagrangian of the system and can make connection to another quantum system too. Okay. So these two systems compared side by side, okay, and they can even use one to simulate behavior of second one. So a couple of directions look into, for example, okay, we can study the behavior of few particles, okay, looking into dimer and even trimer physics. And the one direction make connection with nuclear physics. Okay. Look for some of the interesting predictions by nuclear physics, say ephemeral physics. Okay, that's first discussed in nuclear physics, but now it's been our kind of research direction for the past 10 years, okay, looking at this ephemeral physics based on co-atoms. Second direction, we developed this look into the dynamics of this quantum system driven far from equilibrium. Okay, can make connection with some cosmological model to study, say, the structure of a microwave background, the radiation, looking into the so-called Sakura oscillations or keyboard mechanism, and even kind of a simple model inflation to see how structure emerges, okay, from an initial uniform quantum system. More recently, looking into how we can potentially simulate unroot radiation. So this part I'll mention in a little bit. And also other connection in condensed matter, right? Okay. And looking into exotic quasi-particles or some of this particle kind of jet formation. We can also see some kind of jet formation in co-atoms. And some of the technique we actually learn from particle physics, how to do pattern formation, how to do machine learning pattern recognition to identify the jet structures. Okay. All right, so at this point, I'd like to mention there are also similar kind of interests in our community, in particular in Israel. We have been interacting or learning about similar physics, starting by some of these physicists. For example, Lev Yakovich, we actually have a kind of collaboration. He's from Bar Ilan, okay, looking into three-body physics. From Weizmann Institute, I have a lot of interaction with Neil Davidson, okay, looking into this BEC physics and recently kind of mediated interaction when quantum system embedding another quantum system, and then there's a kind of a media interaction and be connected to quantum magnetism, that RKKY mechanism. That's something we've been very interested us very much. Also, not too much collaboration, but we're share similar interests with your colleague Justin Hart, looking into this say Hawking unroot radiation. Our version unroot radiation is a simplified version of Hawking radiation. Okay, that you can see there's some connection in later slides. All right, so mention the connection with kind of this physicist Israel. I had to mention that it's my first time visiting Israel last year, last December. At the moment, I'm so grateful I was given the opportunity. I cannot imagine how how such a kind of conference can happen. Not this year, maybe not even next year. But it was a fantastic opportunity for me to visit Israel. Just a few months before this pandemic. All right, I had a great time, and this is organizer. All right, let me begin the story. Okay, so the story began in 2017. Something unexpected happened. I remember in that time, the early 2017, I was teaching, I think something like electronics and so on. It's a pretty heavy class with the lab and the lectures and so on. And my students essentially working on some kind of secret project. They didn't, according to what they said, they didn't have time because I'm busy and they're also busy in the lab and so on. These are the postdoc, Anita Guy, and also former student Logan Clark and Fun Day. Eventually, in March, they revealed what they've been working on. They hid this from me for a couple of weeks because they didn't know what to say. They saw something really bizarre. Okay, and they see, here's a report on the so-called secret project. We made an exciting observation and we wanted to try to understand it somewhat before bothering you. So,
Cheng, do you by any chance have some earphones, because your sound is coming in and out, and it's a little, yeah, it's kind of fading in and out. And, yeah, maybe it'd be better if you have some sort of microphone. Sometimes a laptop microphone does that.
I can see if I can try another computer because I actually do not have a microphone here.
I mean, or yeah, maybe you should get a bit closer to the. Just that the sound is coming in and out. It's a bit
I
hard.
see. Let me try to stay a little bit closer, and I'll also try to speak a bit slower to see maybe that helps.
Okay, thank you. Mhm.
So here is the report from my students and the postdoc. This is what they see. You can see as a function of time. This is our regular BEC. Okay, BEC is a Bose-Einstein condensation of atoms, and then they are very dense and they've been focused, localized in the trap. So let me see if you can see my laser pointer.
We see your cursor, yeah. But
Yeah,
not
see
the.
the cursor. It's actually funny. Let me see this. Let me get the laser pointer working.
We see the cursor. It's fine. Don't worry.
Oh, here it is. Yeah.
So you see the t equal to 0. That is a regular BEC. And what they did a so-called wiggling ramp. I'll explain that in a moment. And then suddenly we see these very thin needles coming out of the condensate. That is so. I've been working at that time. I've been working on BEC for like about 15 years. I had never seen anything like this in my life, and so did my student. We had no idea what's happening to the condensate. Why there's such kind of thin needle like laser jets coming out of the condensate? So to be honest, it took us about almost 5 months to really figure out why exactly is happening. And by the end of the end of the year, we were able to publish this paper, and we call this Bose fireworks because the way the atom shoots out of the condensate, forming this kind of thin needles, really looks like a fireworks. Okay, and this is coming from bosonic atoms, so we call it Bose fireworks. And this is the beginning of our exploration, something that's unexpected. To me, that's one of the exciting aspects of doing experiment. We're hoping for some time, at some point, you see something interesting happening that's never been predicted. As we can just try to do more research, try to figure out what happened to the particles. So to me, this is kind of like an exploration into a new world. Okay, after now this is about 3 years ago. So in the past 3 years, looking into this phenomena, okay, we feel like we're kind of entering into a new world. If you are familiar with this film, it's called this Avatar. You go to the new planet. Wow, look at that. What is that? If, for example, imagine you are the zoologist. Okay, look at that. Is that a mushroom or is that a kind of this jellyfish? Okay, so there are infinite number of topics to study, and you feel like this is there's so many things to work on. Okay, so I hope I can share some of this excitement and some of the exploration we have gone through in the past 3 years. All right, but first let me show you how what is the recipe to create this kind of Bose fireworks. Turns out there are only 2 steps. The first, you need to create a thin, uniform condensate. So what we do is that we provide this kind of laser trap. Okay, the green one is a hollow beam. Okay, so there's nothing in the middle. Okay, so you can think but the green light essentially provide a barrier so atom cannot escape. And the other red laser beam provide a vertical confinement. And we have very strong vertical confinement, very weak horizontal confinement. So what we prepare is a homogeneous 2-dimensional system of atoms. And when you go to very low temperature, now they can condense, they go to the lowest state, the lowest quantum state in this trap. And that's called BEC.
It's all in optical trapping or?
Yes, it's all based on optical trapping. So the green light is coming from one laser, and the red light coming from another laser.
Mm-hmm.
Particle being confined in the space.
And how thin is it?
So the sample is the radius about 20 micron, and the thickness is about half a micron, 0.4 micron. So the aspect ratio is roughly about, say, 60:1 or 80:1. Okay. All right. The second step, okay, what my student did is the following. What they try to do, they try to control the atomic interaction. Okay. So interaction is characterized by this the so-called scattering length. When the scattering is larger, then you have the repulsive interaction. When scattering length is negative, you have attractive interaction. And in this figure, it shows how the interaction is suddenly modulated starting at t equal to 0. Okay, and in this figure, it turns out in our experiment, ADC, the offset is small, amplitude is large. So for half the time, interaction is repulsive. The other half of the time, interaction is attractive. So from the point of view of quantum simulation, this is a strange kind of experiment. We never really think about any material, the interaction between atoms can be oscillating between the attractive interaction, repulsive interaction. So why did my student do that? Well, somehow they just try it. Okay, they're thinking about some other project, but accidentally they kind of apply the modulation to the magnetic field, and the magnetic field modulation lead to the interaction modulation. Okay, all right. So the whole thing is accidental, and this is a recipe they follow. So let's try to look at this 5-way emission more closely. So t equal to 0, that's when we apply the modulation. You can see after a few milliseconds, you start to see this particle coming out of the condensate. Right. In some later time, you even see some structure in the middle. And then you can start to see this particle leaving the condensate. They form pretty thin, kind of narrow jets, okay? Like a needle coming out. Right. And this is a top view. Remember, this is a 2-dimensional sample. So if you look at the system in the z direction, now this is the structure you see. We also have a camera from the side. If you look at the system from the horizontal direction, okay, this is a much longer time scale, but you can see the emission is mostly on the horizontal direction. Okay. Not much is going on in the z direction. So our camera in the z direction pretty much captured the full kind of dynamics. All right. The first thing this, so there are a lot of things we can study. So this, before we really figured out, the first thing my student did is trying to figure out how energetic are these particles coming out of the condensate. So in the beginning, we're about kind of 100,000 atoms in the condensate. And then each jet, you see here, contains about a few hundred atoms. Okay, few hundred atoms. So if we can just compare this, the images at different time, we can calculate and determine the kinetic energy of the atoms. Okay. And actually, when my student did the experiment, my first guess is that, well, this is like photoelectric effect. If you try to excite the particle, and then the excitation should carry the same energy as h bar omega, where omega should be the modulation frequency. But it turns out my student proved me wrong. It turns out the kinetic energy of the particle leaving the condensate is only 1/2 the modulation frequency. Okay, it turns out excitation energy is 1/2 h bar omega. Okay. So you can see horizontally modulation frequency goes from 0 to 10. Vertically, atomic energy goes from 0 to 5. So the slope is actually 1/2. So this lead to this. When we see this, immediately we kind of went back to the image. We can start to see perhaps there is something a bit more interesting in in terms of this emission. It looks like perhaps there's some kind of a correlation. We are doing the kind of excitation into pairs. You can see particle here is strong, here also stronger. There seems to be some kind of pair excitation. Okay. It's not a single particle excitation. Okay, so likely this you excite particles in pairs. Okay. And then the emission also happens in pairs. On the other hand, if you do more closely, some of them they don't really see completely kind of symmetric. So there's a strong jet going to the left, but you don't see something like that to the right. So there's some correlation, but it's not 100% clear. Okay, the second thing my student did is trying to change the modulation amplitude to see how strong we need to modulate in order to see the emission. So the simple conclusion from this study is that the fireworks only appears if you modulate your interaction above a threshold. Okay. So right here you can see the modulation amplitude. This is how strong we do the modulation. You can see for any kind of frequency we apply the modulation 1.3, 4.5, 8.2 kilohertz and so on. There should be some kind of threshold. We can see below the threshold there's a very weak excitation, also no jet structure. Above the threshold, then jet structure emerges quickly, and also kind of this had a much stronger kind of slope, much stronger dependence, okay, on the amplitude. So from this, we kind of start to have a kind of classical picture. I have this assumption that you are kind of exciting a liquid in this in equilibrium, right? You might have seen images like this, okay? And then you also see this kind of almost like a jet structure. These are droplets, small droplet form. In the classical system, we believe this the structure is due to some kind of hydrodynamic instability. But in our case, these atoms are gas. These are quantum gas. We're actually pretty sure there's no kind of surface tension. Okay. It's not quite clear where this instability or this structure is coming from. Okay. So that's the most intriguing kind of aspect of this. And also pose a question, how do we characterize the emission structure? It looks like they form jets. Okay. How strong are these jets, and why is the structure, okay, why is, for example, the width and the length and so on of the jet structure? So this is what we did. So what we did is that we try to only look at the signal in this fan area, in this ring area. And then we try to define the density distribution as a function angle, emission angle. Right, and we can try to see whether there's any correlation between the emission along theta and emission along theta plus phi. Then we can evaluate the so-called correlation function to see whether there is a correlation between the emission at different angles. And then we can average over all pairs, okay, separate by phi. So we sum over all theta, okay, but phi will be a control variable we can put in. So this will allow us to see whether the emission are correlated. It turns out to be a very important step that leads to this a much deeper understanding what leads to what results in this the structure we see. All right, so based on this definition, the G2 is a density correlation in angle in the angular space. And here's the result. This is a G2 as a function of this relative angle phi. So you can see for very small angle, we see a pretty strong correlation. And G2 function is normalized properly such that if you see G2 equal to 1, that means there's no correlation, equivalent to random emission. So it looks like for most of the angle, there's almost no correlation, except for very small angle within about 3 degrees. Then you see high degrees of correlation. Okay. All right. So I mean within 3 degrees, either they emit or they do not emit. There's a strong correlation. Another correlation peak we see is at 180 degrees. So this more or less confirm our observation. There seems to be some kind of correlation along 0 and 180 degrees, 0 and pi. And this kind of correlation is also called pi peak. Okay. So when the relative angle is pi, now they seem to be correlated. However, our simple theory, and in 2017, we're very simple theory. We said, well, if the excitation really push one particle to the right, then in principle, according to momentum conservation, there should also be a particle going to the left. In principle, they should be perfectly correlated. So our model give a kind of a fully symmetric line shape at around 0. Okay, that's when 2 emission within 3 degrees, and also at 180 degrees. So kind of opposite kind of this emission, 180 degrees. Our experimental observation is much smaller. Okay, when we're still trying to figure this out, it turns out this my student also looking into how this emission occurs as function of time. So this, once you can define the jet to be 3 degrees, then we can start to essentially divide 360 degrees by 3. So we can essentially consider there are 120 jets. Some jets are stronger, some jets are smaller. So we can divide all the emission particles by 120. We can determine how many particles per jet. And jet also corresponds to 1 mole. So we can say how many particles per mole. All right. So from this experiment, we can see if you just try to drive the system as function of time, you see starting from 4 milliseconds, we start to see that's the earliest time we can see the emission. And later, it looks like the population per mode increases kind of almost exponentially by about almost 1 order of magnitude. So it seems to be some kind of very fast exponential growth in the first few milliseconds. And later, it kind of tapers off. It just kind of saturated. And this behavior, the saturation, we realize is coming from the depletion of the BEC. So when you emit too many atoms, eventually we deplete almost at 60% of the condensate. Now with the exponential kind of growth, we can extrapolate to t equal to 0. Okay. Then we reach a value of about 1 particle per mole. Okay. And that's quite very close to the quantum limit. Okay. Essentially kind of 0-point fluctuation, how many particles in 1 mode. Okay. There's always like a harmonic oscillator. And because of the pair production, so you have a 1/2 particle in 1 mole, another half in the other mole. So turns out this the prediction is 1. So from this experiment, we are essentially kind of think the emission is likely coming from quantum fluctuation. So this structure we are seeing is amplified, is coming from quantum fluctuation being amplified by almost a kind of almost a fatal 100. Okay, right. And I'm going to show you more evidence how we compare this our observation with calculation.
Conclusion from seeing that you can extrapolate this to 1 in the limit of slow driving.
That's why you a short time. Okay, so right here,
right
here we fix the strength and only change the driving time.
Driving time is driving inverse frequency or just total time?
The total time, that go back to the definition here. So this is driving time, okay, and the frequency. So there are 3 independent variables: amplitude, frequency, and the time. So in that experiment I just show you, amplitude is fixed, frequency also fixed, and then we only change the driving time. So the equivalent to this figure. So at different time in the beginning, you see no emission, and emission gets stronger and stronger as a function. Okay, does that help? All right. However, one thing still puzzles us. How come there is the pi peak? If there's a pair production, how come the pi peak is so much weaker? Right, we didn't understand this part. This in 2017. But turns out this just 1 year later, this high energy theorist contacted us. He said that, well, the spectrum you see is very, very close to the kind of jet structure he studied, and he was in this CERN. So he refers to us this measurement, is so-called jet structure in this high energy collider. They also see kind of jets. In a very simple picture, you can think about in terms of, for example, proton-proton collision. Then many fundamental particles being created, and some of the particles being created, like pion and so on, are also bosons. This boson can stimulate more bosons going into the same direction. It turns out they form jets. And also because of this momentum conservation, you will expect this correlation at pi. So that's why you see there's a peak. This, I'm not sure why you don't see the laser pointer. All right. Anyway, so you can, there's a pointer. Okay, so this is a peak of pi, that's 3.14. they also see that's a strong correlation around 0. Autocorrelation is always is strong, and the pi peak is also compromised. So it turns out in the high energy system is much more complicated. This is due to some of the multi-collision process that due to hydrodynamic behavior. So the correlation between jets is broadened and also suppressed due to this many body collision, or hydrodynamic process. So he wrote this paper to compare this our experiment jet emitted by a driven BEC to this jet structure, jet physics, and particle physics. Certainly, our system is not so complicated. We don't have so many fundamental particles in our system. However, we see very similar structure. Let me see. Looks like my frozen. All right.
Is there some sort of sum rule that says it's from momentum conservation that the weight under both peaks should be the same?
Yes, indeed. That we check within our experiment uncertainty. You can see this the area below this below the two curve essentially agree to 95%. So
I see. Thank you.
All right. So motivated by that, my former student kind of done the second kind of this study, trying to look for any kind of a new structure in the system, other than this apparent pair correlation. So this is my former student Lei. He is motivated by some of this pattern recognition kind of this idea. They say, all right, our system has this kind of azimuthal symmetry, cylindrical symmetry. Okay. And we can repeat the experiment multiple times. And then we can try to rotate, try to define some kind of axis according to the emission. For example, in this direction, you can see a pair of strong emission. In the other image, the strong emission says along this horizontal, along this direction. Let's try to use this rotational degree of freedom as a free parameter to rotate individual images. For example, in our experiment, we compile 200 images and we define 200 variables, theta 1, theta 2, theta 3, theta 4, and try to rotate them until they match. What does that mean they match? So the strong emission along this yellow line, okay, and try to also orient the emission in the second image along the same direction, and third one along the same direction. And this is a process that requires 200 free parameters, so you can send this whole thing into this computer and run it overnight, and try to see whether the computer can identify some pattern that's shared by this by all these experiments. So you can see in the beginning, okay, the axes are randomly oriented. So the purpose is trying to put them together, align them together. All right. Eventually, he told me that he actually recovered a new hidden pattern. He called this a turtle pattern. I'm going to show you how the turtle pattern comes about from the emission. So what you are seeing here is the average of 209 images. If you do the averaging, okay, without the rotation, you do not see any structure. Let me see, how do I start the movie? Let me see, maybe I need to. Hey, I would really like to show the. Okay, I'm going to show the movie this way. And then, but after you apply this kind of a pattern recognition, this algorithm, you can see after say several hundred or 1,000 iteration, you try to overlap and try to orient this individual pattern, trying to see, you can start to see a new pattern start emerging. This algorithm turned out to be much more powerful and also kind of this efficient to identify all the possible correlation in the system. Let me play this again. So this takes about 8 hours, but I just shorten the whole 8 hours optimization into a few seconds. You can start to see now some kind of structure emerges. The strong emission in this direction, In addition to this strong emission, the accompanying kind of emission along this direction, so that's the 4 legs of the turtle. 1, 2, 3, 4. As well, there's a kind of a small peak you can see here, head and tail. Okay. Also, some other structure you can see here. All right. So, so because of this, if you work on this project for a long enough time, now you start to imagine, okay, this actually is an animal. So we try to call these 4 peaks are the legs of the turtle. This is the head and tail. Let me continue. All right. So we had this new release from University of Chicago. Okay, so we identified this new interesting kind of structure from this emission of a BEC. So in essence, each image consists of many such turtle patterns. Okay, what we see is this turtle pattern kind of overlap. Okay, some stronger, some weaker, some even multiple turtles, but they're all in different direction. If you average them, then you don't see anything, or you don't see the structure. But once you orient, then you can see the structure. That you have 5 fingers. You overlap them together, then eventually you can see the fingers. But if you just average, then you don't see the fingers anymore. All right. So seeing this structure is one thing, but as a physicist, you want to understand where this is coming from. So I'm now going to just use a simple word to and with kind of a math on the side. With an expert, you can probably recognize what's happening here. Okay. So let me first talk about what we discovered in 2017. It's a pair production process. Pair production means you have particle in the condensate. Remember, it's a dense sample of atoms, and then they can interact. And then once you do the modulation, you excite the system. Okay. But because of momentum conservation, one particle go to the right, the other particle had to go to the left. So that is a pair production, and that's described by this Hamiltonian. So you create particle with momentum k, accompanied with another particle in momentum minus k. And this process enhanced in a condensate by the particle number n naught. N naught is the particle number. This is a primary process. And then it turns out there are these other secondary process that lead to the 4 legs, 1, 2, 3, 4, and also 5 and 6, head and tail, as well as these 7 and 8. These 2 peaks are also quite clear to us. So how do we understand this additional secondary structure? It turns out what happened is, I'm going to play this movie. So you see 2 particles, one in the condensate, one in this direction, they can collide. And in momentum space, one can have a receive momentum kick going to the left. The other one receive momentum kick going to the right. Okay. So this process can be described by this Hamiltonian. It's a higher order process because it's only being enhanced by square root of n naught. So it's weaker than the first term. Okay. However, it's still possible to be seen in all this. Now, let's also try to understand head and tail. The head and tail can be understood this way. You have 2 particles at this location, and then they collide. Because of momentum conservation, one particle is being scattered in the forward direction. The other particle being scattered back to the BEC. This process also enhanced because BEC is involved. It's also enhanced by square root n naught. So it's the same order as the process I just mentioned. So these 2 processes essentially together determine the structure of the turtle, okay, including the legs of the turtle and also the head and tail.
Why is there this kind of breaking of symmetry when you look in the individual?
Yes.
Yeah.
Right. So each process, so the symmetry breaking already happened in the primary jet process. So what happened is the process enhanced, also stimulated, is a kind of parametric amplification. So when some particle going in the forward direction, you will stimulate more particles going in the same direction because these are a Bosonian stimulation going on. Okay, that's a very good question. Is this stimulated process lead to the enhancement? Your stronger jet will lead to more scattering into the same mode. Okay, the weaker jet will always lag behind. All right. Okay. So this is some direction we'll continue looking into. Okay, very recently we can see even more complicated structure. We start to work with the theories, this case 11, okay, to look into the emission. So this is some of the prediction. Sometimes you can even see the jets with a kind of chirality. Okay, so you can see in these figures, sometimes you can even see spirals, okay, coming out of the condensate. These are experiments. You can compare with this theory. So there are also substructures in both in the byway emission. All right. So by this time, it turns out there's yet another kind of connection with another colleague of mine. That is, let me try to get the system going. Okay, let's wait for another moment. We'll come back. All right. So, and in a discussion with another theorist, this Tom Whitten, he studied kind of soft matter and hydrodynamics. He said, well, in principle, you should be able to see even more interesting structure. For example, triangular wave and or hexagonal wave and so on. So would that be possible? Also be can we also produce that in the quantum gas? So this is something called Faraday wave. Before I go into the math, I'll just show you. I'm hoping I can show you this video. Looks like the system. Okay, good. I can show you the Faraday wave. So what you are seeing is a thin dish of water, and we vibrate the water in the vertical direction. So in principle, nothing breaks the kind of rotational symmetry of the system. However, the video is not showing. Okay. So how about the following? I would recommend you to look into this. You can just search on YouTube, say Faraday wave. What you'll see is that in the beginning, the water surface is flat without any structure. If it starts shaking, for small shaking amplitude, you will see some kind of waves, but it will be symmetric. But once you go to higher and higher kind of shaking amplitude, you start to see structure emerge. Sometimes you see a square wave, okay, a square lattice. Sometimes you can see hexagonal lattice, okay, or triangular lattice, depending on how you look at it. Okay. So that also is a symmetry breaking process, okay, but just in our case, it's more coming from quantum fluctuation. Okay, in the classical kind of system, probably more due to the imperfection of system or thermal fluctuation. All right, so for the expert, let me quickly go through the kind of our way to describe this pattern formation and also nonlinear kind of wave, this process. Essentially, the particle can collide. Okay. Quantum mechanical interaction is described by to leading order by this 5 to the 4th power, proportional density square. But now the interaction parameter is being modulated. Okay. And we can also write this interaction in the momentum space. And what you see is very intuitive. You have two particles coming in, say K3 and K4, momentum K3, momentum K4, and scatter into two new directions, K1 and K2. All right? And because there is a momentum conservation, it's also called phase matching condition. So the K1 plus K2 equal to K3 plus K4, just like kind of this two-body collision we learn in mechanics. But also because of the external driving, so energy being transferred to the system. So we actually allow the energy to increase or reduce by h bar omega. So it provides this kind of constraint, put it into this Hamiltonian. Okay, then you can try to see how this particle is being excited. And leading order, as I mentioned earlier, is a pair production. So in the beginning, you have a zero momentum. And then you can create particle with this one to the right, one to the left. That's the leading order process. And then higher, the next order, okay, can be can be written the so-called nonlinear wave mixing. So you can also see the breakdown of one particle into two particles. Okay. But because of momentum conservation, you can lose one particle with momentum K1 plus K2 and create two particles with the momentum K1 and K2. All right, if you just perform the truncation at this point, only include these two terms, you can derive the so-called quantum nonlinear amplitude equation. It's a quantum analog of Faraday wave, this kind of a Hamiltonian that show you how the nonlinearity goes into a kind of a quantum many-body system to this order. All right. So given that equation, we try to kind of try to be my students try to be creative. How can we create some new type of patterns? For example, how can we create a triangular pattern? They tried for a couple of months all kind of different ideas, and this one works. So you can see this is how we perform the modulation. We no longer perform a simple sinusoidal modulation. We first perform this in the first 20 milliseconds, we apply sinusoidal modulation, and followed by this kind of more complicated modulation that contains the second harmonics. Okay, right? And this is the pattern we see. In the beginning, with no structure, t equal to 0. After the first phase of modulation, we see some kind of linear structure. At the second phase of modulation, we start to see kind of this kind of funny pattern. So this pattern may be difficult to see what kind of structure that is, so we can do the Fourier transform. You can see in the beginning, there's no obvious structure. And then at the 22.6 milliseconds, you see the pair production. And then after 45 milliseconds, we actually see this hexagonal structure coming out. So that suggests there's a hexagonal lattice, okay, in real space. This is just a Fourier transform of the density distribution in real space. Okay. And we can also do the so-called pattern recognition in real space. I will kind of skip the details and show that indeed with the pattern recognition, we can indeed kind of create kind of structures, a triangular structure or hexagonal structure, depending on how you look at it. Okay. Or you can create structure with kind of more like a square structure. So system will either have a 6-fold symmetry or 4-fold symmetry, depending on how you modulate. Okay, and that this we can compare with a theory, and we'll continue going in this direction. Okay, to see maybe there are new type of structure we can create beyond 4-fold and 6-fold symmetry. All right. One more direction we're looking into is that this is another kind of serendipitous kind of observation that our emission, the firework, can somehow connect to the unroot thermal radiation. So that for this project, we work with my colleague Robert Ward. In general, if I studied gravity, you know, he's written kind of key figure written in the kind of this textbook, and working on this GR and many related issues. And the unroot radiation is a simple way to reproduce Hawking radiation. So the basic idea is the following. So if you consider a vacuum in the inertial frame, now if you try to go to a non-inertial frame, the simplest non-inertial frame will be an accelerating frame. In an accelerating frame, the vacuum will no longer look like a vacuum. Okay. And Unruh, I think in 1976, he did a calculation to show that if we can accelerate a system with high acceleration, for example, with something like this, okay, then you can the vacuum state will behave as a thermal state, and that is the temperature. We call Unruh temperature is related to the acceleration of the observer, okay, and everything else is just fundamental constant. H bar, C, and KB, and so on. For example, you can plug in the number. If you want to see an emission of 1 microkelvin, you will need to go to an acceleration 2.5 10 to 14 meter per second. This is enormous acceleration. So in the lab, if you want to do this in the lab, it's a very difficult. In this some acceleration like this, very difficult to create. Okay. In recent years, people try to use a kind of petawatt, this laser system, pulse laser system, Okay, you can, for a very short time, you can accelerate electron to acceleration, but I think it's just a few order magnitude away from something like this. And emission 1 microkelvin, very difficult to see. And the reason this is linked to Hawking radiation because the equivalent principle. Equivalent principle says that if you are in the moving in the accelerating frame, it's similar to your you put yourself into a gravitational field. So in the presence of strong gravitational field, okay, the vacuum can also look to this the observer as a thermal source. There was thermal excitation and so on. All right. So how did it connect to this our 5-way emission? So I need to acknowledge the contribution from our former postdoc Jia Zhong. He work we together work with Bob Ward trying to figure this out, figure the math, figure out the math. All right. In our system, we had no gravity, we had no strong acceleration. All we do is try to evolve the system. Okay, based on this the Hamiltonian I just showed you. But it's but turns out we recognize the evolution of the system. Okay, the time evolution of the system in our case is more or less the same as the frame transformation. The frame transformation going from vacuum in the inertial frame to vacuum in this non-inertial frame can be modeled by this evolution operator. Okay. Evolution operator can be controlled by Hamiltonian. So if we can control the Hamiltonian in the proper way, say given this form, essentially a peer production form, with a proper GK and so on, then the evolution of the system can be mapped to the frame transformation of the system. So what we see in the lab, okay, can be modeled as a frame transformation of the vacuum into this higher acceleration.
I'm sorry, can you repeat what transformation?
Okay, the transformation in our case is on the right-hand side, is the evolution operator.
Yes,
so,
but what's the R?
Huh? So right here, the evolution operator is given by this exponential to a power of minus I. This is Hamiltonian. Tau is the time. Okay, tau is the time. Okay, so when the system evolves in time, it's similar to you boost the system to higher acceleration. Okay, and
why does this describe acceleration? Maybe obvious.
It's a mathematical identity. Yeah, this transformation is the same as a frame transformation into the accelerating frame. Okay, this is just a mathematical statement. Okay. So the mathematical structure of this transformation into a non-inertial frame is the same as evolution operator with a proper engineered Hamiltonian.
In the case of Unruh, you know, you basically get a thermal state because you trace out in one of the Rindler wedges, but yes. But here it's completely unitary, right? You don't get
yes, it's completely unitary. So if you trace out this kind of if you trace out this all this excitation in opposite direction, you also show in principle entropy remains 0. However, if you perform a local observation, so the idea is the following: there's emission going to the right, also emission going to the left. If you perform local measurement, then you see some kind of finite temperature.
I see.
But, and why does this transformation not commute with the particle number?
It does commute with the particle number. Okay, so
I mean there is A dagger squared, so it does not commute with A. With so, it doesn't conserve particles.
I think it just dilutes.
Right. So right here, in principle, we lose 2 particles in the condensate, but because we have a lot of particles in the condensate, and replace the condensate operate creation and annihilation operated by C number. So this is essentially under the limit when there are many particles in the condensate, and then there are few small fraction of particles being kind of created into free space, or global approximation.
Okay.
Okay, and then if you compare the math, eventually you can show that given the proper coupling constant GK and the interaction tau, Okay. Then the acceleration we are trying to simulate can be given by this functional form. So experimentally, if you want to go to higher acceleration, it turns out you can go to larger coupling strength and also longer evolution time. So these are the control parameters we have on the experiment. And then in principle, the emission should also be thermal. Okay, should also be thermal. So that's something we can check experimentally to see whether the emission is a thermal has a thermal structure. Okay. So with this idea, we started this project in 2019. Okay, we look at 2018. Sorry, we look into the kind of emission structure. So here, let me skip the proof. All right, maybe I should mention a little bit. So this is Hamiltonian we write down. Okay, so if you try to write this interaction term, okay, and apply this Bogolov approximation, we get the effective Hamiltonian. You see the pair production. Okay. And then given this pair production Hamiltonian, you can try to write down the solution. If you start with a vacuum state. So here, what does that mean vacuum in our case? Vacuum means a condensate with no excitation. Okay. We assume all the particles in the condensate essentially is the vacuum. Okay. The system free from any excitation. With this Hamiltonian, and then you can write down the solution at a later time. Turns out this can be analytically solved. Okay. You can see the excitation indeed has a thermal distribution, where En is the energy of the system with N particle in one mode and N particle in the other mode, because this is a pair production. So always the N particle in the mode with momentum K, and N particle with N particle in the other mode with momentum minus K. So N and N. So if you trace out only one side, okay, if you only look at the first quantum number, perform measurement on one side, then it looks like you get this thermal distribution. All right, so we can try to verify whether we indeed can see this kind of thermal distribution. So let me see. Okay, and here's the math, how you think about the problem in terms of transformation from inertial to non-inertial frame. Perform the transformation going from the I probably try to skip this. Okay, in the Minkowski space in the inertial frame, to render the space with a finite acceleration, small a acceleration here. The transformation can be written this way, and you can write down the creation annihilation operator in the two bases, in the two frames, in the following way. And it turns out it can show that this transformation indeed will convert the vacuum state in the Minkowski space into a vacuum state in the rendered space with connected by this operator. This operator can be understood as an evolution operator with Hamiltonian that contains a pair production. All right, so experimentally, so this we want to test the prediction. So what we try to see how many particles are there in one jet. So you can see from the earlier picture or image, you can see some direction is strong emission, some direction of weak emission. It's very random. So here we can perform the experiment many times and calculate the probability to have N particle in one jet. Okay. And what does that mean? One jet? One jet is 3 degrees. That we can determine the width of the jet from the correlation function. For example, at t equal to 0, then a 0 particle in the jet. You wait for 3 milliseconds, 4 milliseconds, and 6 milliseconds. You can see the population per jet, okay, is moving toward higher and higher number, but there's a lot of fluctuation. Say after 6 milliseconds, some jet had this 100 particles, some jet had only like few particles. So this distribution very, very broad, and it's also thermal. And I should mention at t equal to 0, there should be no emission. However, our system has our signal noise is limited, so we cannot really measure particle down to single particle. So the width is coming from our detection uncertainty. But you can see the whole thing shifted to the right. So and the solid lines are the fits, okay, based on our thermal model convoluted with the detection uncertainty. All right. From here, we can once we know the thermal distribution, we can assign an effective temperature. So you can see from 0 to 6 milliseconds, the system getting hotter and hotter. And that is the temperature, that effective temperature we can derive from the thermal fit. Okay. And now in here, we try to plot the temperature versus this mean population, the mean population of atoms in one jet. Okay, so, and this compare with this unroot prediction, the formula I showed earlier. We can also show the entropy power. I will skip the entropy power, just focus on the temperature. And then see there's a pretty good agreement. You agree to about 95%. So what's happening here is that essentially, even though the evolution is a unitary, in principle, okay, the system doesn't reacquire the entropy and so on. However, if you perform the measurement locally, like what we did on the camera, okay, we perform look at the particle on the right, particle on the left. Okay. And such kind of projection to the local observable, okay, will lead to a very broad distribution of this population in the jets. And that distribution traces out thermal distribution. And what that means is that if you are the observer, okay, only on one side, okay, of the emission, then you will feel there's a heat wave, there's a thermal radiation coming toward you. Okay. And so this is a very interesting case. That is a thermal if you have performed a local measurement, but globally it's a unitary transformation that convert the vacuum state into this essentially effectively into a vacuum in the accelerating frame. All right, and if we wish to know more detail, this paper just published last year, and we also look further into a correlation to show that indeed the emission, even though it looks thermal, okay, but still has all the memories of quantum nature. It's a quantum evolution process, okay, that establishes this correlation at long distance, okay, because of pair production. All right, so the last kind of a line of research that happened earlier this year, okay, and but for that I want to give you a little bit background on these molecules. You know that this laser cooling on atoms has been working very well, but on molecules are much more complicated. There's a lot of progress in recent years. And for example, 2 years ago, people were able to kind of combine two atoms, pair them into a molecule. And also the last year in Jun-Yi's group, they form a fermionic quantum gas of molecules. Okay, the molecule of the fermion. Okay, and there's a roadmap how we can bring the molecule closer and closer to quantum degeneracy regime, going to higher density and lower temperature. And I think GILA is the only group so far that can create this kind of Fermi gas of molecules. Okay, and the BEC of molecule have not been created. However, there's a lot of kind of interest into the kind of pairing. For example, in terms of BEC, BCS crossover. You can pair fermionic atoms into molecules. And those kind of molecules form a condensate or can form Cooper pairs. But for bosonic molecules, that's what we are working on. It's very different. So bosons are different from fermion in the fundamental ways. So fermion, they do not form condensate. You need to pair them to form condensate. But for boson, the similar prediction, kind of atomic atom can condense. Molecule can also condense. But such kind of transition had never been seen. Because these kind of bosonic molecules typically are very fragile and then they are unstable. And even though this has been predicted for over 15 years. So people had not been able to pair these atoms into molecules. Bosonic atom into molecules. All right. So how is this related to a fireworks I'm talking about? If you look at the Hamiltonian, you can realize this is very similar to what we just studied. So you can see two atoms, they can combine into molecules, and the reverse process in one molecule decay into two atoms is also a pair production. So in the quantum regime, you have two fields. One is atomic. One is the atom, atomic field, the other one molecular field. So there's sort of pairing and unpairing. Okay, in a sense, in a way, it's very similar to this kind of pair production. Okay, pair production and also the reverse, the pair annihilation process. Okay, so motivated by this connection, this is something we did since the second half last year. All right, we also prepared this, remember we have this thin two-dimensional sample of this condensate. We are doing the same experiment. This time, we want to induce the pairing, essentially try to compare two particles into one molecule. And what we do in the so-called phase bar coupling, essentially pair atoms into molecules by introducing the resonant coupling between two atoms. Okay, this is atomic state. Okay, and here the potential is, say, molecular potential is a cartoon of molecular potential. But then if you can somehow couple atoms into molecules, that will lead to the pairing. Okay? So the basic idea is that if we can do this, okay, and they can convert two bosonic atoms into one bosonic molecules, and this is a conversion between two quantum fields. Both are bosonic, but through this pairing process. And then we work with Paul Julian van Nist. Okay? He knows a lot about this molecular state, okay, to identify the good molecular state for us to perform the pairing. All right. So here's the result. I'll quickly go through the result. On the left-hand side, this is atomic condensate. You can see the uniform atoms in this circular track. Okay? The density is roughly 45 and so on, right? Rather uniform. After the formation of the atoms, then we induce the resonant pairing, okay, by aligning the atomic state to a molecular state. Okay? This is done by magnetic field. Okay? After that, this is what we see. These are molecules. Okay? These are all molecules. And from very different kind of, the smaller, the fewer part molecule we can form and so on. Okay? Immediately we realize these molecules are created very, very low temperature. In principle, ground state, atom in the ground state should be converted into molecule in the ground state. Right. So we perform the experiment trying to see whether indeed this molecule also forms a condensate. Right. Somehow the computer is hanging. Okay. All right, good. So here is our first set of experiment showing that this, if you look at the equation of state, you can see when you move on to higher and higher chemical potential, going to denser and denser sample, eventually the density of state or the molecule experience some kind of a change, a phase transition into the superfluid. But this transition very subtle. Remember, we're in 2D regime. Okay? So it form a kind of a costly dollars superfluid in our 2D trap. Okay. All right. The same experiment on the atom also see similar transition. Okay. This is a 2D atomic superfluid converted into this BKT, this molecular BKT superfluid. All right, and this is a paper just published a few months ago, and we continue looking into the one of the interesting kind of this process is the pairing unpairing process, and we have shown in this experiment we show the pairing. In the next slide, I will show you the unpairing, the dissociation of the molecule in the condensate.
You know that I like you, baby. You know
Okay, so here we also see if you start with the molecules and then you can see how they unpair back to atoms. So these are dynamics of this molecule in the ground state. And T equal to 0, we suddenly release the molecule back to the continuum. And see, so in the beginning, you see no atoms, and suddenly at t equal to 0.2 milliseconds, you start to see there's a ring of molecule coming out. So the ring of atom coming out. And by this process, we can understand kind of a unpairing process, okay, pairing unpairing process in the bosonic superfluid. Sorry, I think the last few slides, my computer is struggling to show the next slide. And we're currently working with this theories and understand perhaps this pairing and unpairing, okay, can be a simple model to understand this other type of this superfluid where this particle pairing can exchange partners. Particle can exchange partners to form a different kind of superfluid. All right, I'd like to summarize. Essentially, from 2017, this firewall experiment can lead to a couple of new lines of research. One is to study the jet structure. Second one, the pattern formation. This requires some high order process. And we'll continue looking into this some of the very recent kind of predictions. We can perhaps also look into unruly radiation in a different setup, circulation or other type of this. Other kind of essential, but right here, what interests me most is how to see the difference between the thermal state, the local thermal state, and the global quantum state. It's opposite of what you think in quantum physics. You would think globally the system should be classical and locally it should be quantum mechanical, but this system is the opposite. All right, and also with the molecular condensation, try to understand pairing and unpairing in the quantum in the quantum regime. Okay, so finally, I'd like to, for new students, okay, I'd like to acknowledge the contribution from a lot of former and current students. They're essentially going new directions, and explore new connections in the lab. Okay, we have an unlimited imagination how our system can be connected to other phenomena in other physics disciplines. At the same time, you keep our nose to the ground and just based on the system we have, okay, then try to look for any trace. Perhaps some connection can one day be identified. Okay, and I think that's one exciting aspect of to be an experimentalist. Thank you.
Nathaniel, you are muted.
Sorry. Thanks for this wonderful talk. And let's see if there are questions. I wanted to ask about this unpairing, maybe about this experiment. What are you changing when you go into this molecular state, and then do you do anything to go into this, to check this unpairing, or do you just let the system evolve freely?
Right. So yeah. Here's a kind of a simplified diagram of what happened. Okay. So the black line is atomic state. The red line is the molecular state. So if you go to the left side, the lower magnetic field, the molecular state more stable, and then you have the molecular condensate.
I see.
The other side, atomic state more stable, okay, and then you get atomic condensate. So this unpairing experiment, what we do is I start on the left side. We ran the magnetic field to the right side and see how atom appears from the molecular condensate.
I see. So you start on the paired side, the molecular side, and then you switch on the magnetic field, and then you unpair them. I see. But so do you see any interesting correlations in this unpairing, or is it kind of uniform?
So far, not yet. We are still analyzing this we are still looking into this. I believe it should be there, but we just not yet. This is recent, only a few months old.
But it's not. I mean, you did not apply a oscillating field. You just kind of ramped out. Up.
Right. So right here is simpler. Only a kind of a magnetic field ramp is enough.
And these predictions that you're showing are according to what? The
experimental fit is just is our model. Okay. And quite frankly, more recently, we can see some small oscillation. I think there is a certain coherent process happening here.
I see. I see. But the model is just based on this Hamiltonian you showed, where you have like an
right, not quite there yet. Yeah, the Hamiltonian is not too complicated. We are also doing some numerical calculation to understand these dynamics. But we don't have a. This is what we have so far.
I see. Okay. Any other questions? Anybody? I think we ran a bit over time. How is it related to this quark-hadron continuity? I'm not sure I understood.
Right. So the idea is that if you if you can switch partner to pair, whether the superfluid will go through a phase transition or be a continuous transition.
I see.
So in this nuclear physics is certainly much more complicated. People are talking about the multiple kind of quarks and the gluon and so on, and then they can pair in different ways.
Yeah.
The density and temperature, they will switch the pairing partners.
I see. Great. Let's see if there are other questions. Anybody has another question for Cheng? Okay.
Well,
so,
one question is, when you look at this Unruh radiation, do you also look at some kind of a entanglement between the particles, or not really? At least.
Right. That's a very good question. We tried. Okay. However, to show entanglement, we need to go down to single particle. Okay. To really look at single particle. And so far, because the emission go really fast in all directions, spread out, we don't have that resolution. But what we're able to show is that we show that the process is reversible. Okay. So you can see the emission, and then we can show that if you kind of control the modulation phase, okay, I think our experiments that we do the modulation for about, I think, 5 milliseconds. Okay. After 5 milliseconds, if you change the phase of the modulation, if sine become cosine and so on, we change the relative phase, you can see some of the emission actually come back to the condensate. So if you can show the evolution is unitary, okay, then you will show that in principle the system doesn't really gain entropy from this process. Okay. And you can see the temperature goes up and also comes back down. But the reversal is still very weak because this kind of system, many body system, is quite difficult to see even a small amount of reversal. So far, our records is seeing about 15 to 20% reversal.
Okay. Thank you.
Thank you.
Okay.
Okay. So other questions? Okay. So I'd like to thank you for this wonderful seminar. Yeah, and hope to meet you again in the future. So thanks a lot.
All right.
And we'll be uploading the recording to the YouTube channel, if that's okay with you.
Yeah, that's fine.
Yeah.
Thank you.
Okay. Great. Thanks a lot. So see you soon, I hope.
All right. Okay. Bye.